And the next speaker is Michael Jastram. So Dr. Michael Jastram graduated from MIT in ocean engineering, and then that provided him this solid foundation for system thinking. And he began his career in software developing, working as a software architect, requirements engineer, and system architect. And today his passion is helping organizations build physical products at software speed. And that's the focus of his upcoming book. And Michael has world's most distinguished companies from Google to leading automakers as his clients, and has helped lead the way and build physical products at software speed. So welcome, Michael.
Yeah, thank you very much for the introduction, Christos. I hope my screen is fine, and I also hope you can hear me. The first attempt of sharing failed, and I really tried to stick to the 15 minutes that I was allocated. So first of all, thank you to Mark. I mean, that was actually a great starting point, because a lot of the things that you said resonated with me. I have a similar background. I actually have an engineering background. I studied ocean engineering, a domain that has a lot of complexity, hardware and software. But I spent the first 15 years of my career in software engineering, software architecture, before I went back to systems engineering. And the thing is, systems engineering feels quite antiquated after you've seen how software development happens. We had a lot of challenges in the 90s that got solved in software development. But in systems engineering, the building of complex products, we still have, it feels very antiquated. And this is becoming a bigger and bigger issue, specifically because of the need for speed. Especially in Europe, we suddenly see the market pressures internationally. And just to give you an idea of what I mean by speed, I want to introduce to you Stella Li, who is the head of BYD, the Chinese car maker in the Americas. And what she said in an interview is that BYD now has a standard development cycle of 18 months for a car from concept to market, 18 months. And so until recently, the legacy car manufacturers typically were looking at 48 months. That was already established. 40 months is something that is fast. And here is this Chinese organization that builds more innovative, cheaper vehicles at twice the speed. And so product velocity, as I like to call it, is not just an enabler for speed, but indirectly also for innovation. And so this is a huge thing. So the question is, how do we achieve that? And I've seen quite a few case studies, but when I was looking for literature, I realized there is very, very little. And so this is the reason why I actually set out to write the book, which is to be published toward the end of next year. And again, to make it a little more tangible, let's have a look at the typical car component. 50 years ago, you could pinpoint your finger onto where the steering takes place, at this physical component. Today, the car function steering is smeared over multiple components, and this will get even more extreme if we start to do drive-by-wire. And so 10, 15 years ago, we thought we found a good solution for that. And that solution was called systems modeling. And systems modeling works for controlling this complexity. And the complexity is driven primarily by software, but also by networking, team size, and especially when it comes to physical products, compliance. So this is a problem. And we solved that by saying like, hey, we are already using so many design models, computer-aided design for the mechanics, for the stresses, simulations, and so forth, the circuit boards. Why don't we also do modeling for the system? And the most prominent modeling language is SysML, as you all know. And this works. Actually, it works rather well. It just doesn't give us the speed that we need. It helps us to manage the complexity. And organizations that have a lot of complexities, automotive, aerospace, they invested gigantic amounts of money of getting there. And it does work, but it doesn't give you speed, not really. And what I find more concerning, especially if we look at what happened in the software industry, MBSE is not going mainstream, period. It's working, it's expensive, it helps you to master the complexity, but it's also incredibly complicated. It is potentially an enabler for a digital twin, for digital thread. But in practice, I see very, very few organizations that really manage to leverage this. And so this is a problem. And so I started the last few years to look more and more into this challenge and talk to practitioners who had product velocity and try to find out what needs to happen. And I identified 4 principles that give you product velocity. Just to be clear, I will tell you what those principles are, but I will not go in depth, which I cannot in 15 minutes, but I will circle on those and the practices of those that are relevant to the system as model idea. And so the first principle is we need value thinking. We really need to think about stakeholder value. That's our compass during the whole development. And the problem is that in many industries, we simply don't have that. And this is a big challenge for product velocity for established organizations because it requires a culture change. But I'm not going deeper into this today. Another one, which is more interesting, especially with respect to systems modeling, is the design and building phase, architect for flow. You really need an architecture to support that. You need an organizational architecture, but you also need a product architecture. And one of the big problems I see today is that so many products are still treated as projects. You start a project, you do it, you finish it, and then you start the next project. That's not how you get speed. You really need to think about a product and product platform, and having a good systems architecture that is precise in the form of a model helps you with that. The next topic, Mark also talked about the shifting left, integrate early and often and validate. This is something that we are doing really good in software. And now suddenly we also have the tools available for doing that in hardware, with simulations, with rapid prototyping and so forth. And the last one I will also not talk about that much, which is the acceleration phase, which you get during the operation and the evolution phase. And so now I want to look at a few practices in these 4 categories that you need for product velocity that relate to the system as model paradigm. So the first one I want to talk about, and Mark also talked about that is what we call industrial DevOps. And that's actually a great book on the topic, which I find very inspiring, that helps us to really figuring out how we can repeat what we already learned in software to do in hardware. And I showed also some of the same and similar logos that Mark showed earlier on. But what I also added here is CSAND, which I found really inspiring. The idea from Sensemetry, or not the idea, the specific action to put out a repository that is based on open source technologies for sharing your models. So I find that very inspiring. I want to briefly make things even more tangible by talking about a project that I did with a customer where we looked at how we can, for example, make sure that we do more effective dependency management. And so what we did is we looked whether we could use SysML v2 technologies to attach semantic versioning numbers to both providers of interfaces and to consumers. And the nice thing about that is those of you who know semantic versioning will recognize that this allows us to automatically check compatibility of components. And this might be just a small puzzle piece, but I think there are lots of pieces missing, and I hope people are actually working on them. Another principle, and this is now, practice, and this goes to the principle shifting left, is staying runnable, integrating frequently, which is commonly known as shift left. And this is something that I already see happening in hardware more and more often, where you really try to get runnable as soon as possible, for example, by substituting components and then really integrating frequently. A more controversial example of that is the Starship rocket from SpaceX, which had a few nice explosions, but that is their integrate early, and as a result, it's actually very cost effective, even though the explosions don't always seem to confirm that to the outside. But this information gathering and shifting left is extremely powerful and practiced successfully. Another concept, another practice, which I think is so important, is making everything human and machine readable. And one of the big things that I find very sad with traditional model-based systems engineering is that what we're doing there is very often not really machine readable. And most of you who might have worked with SysML know that there's no good interchange of models with V1. The same way that a PDF is digital, yeah, a SysML V1 model is also digital, but really making sure that it doesn't stay in a silo, but that it gets actually integrated and is accessible to machines and humans alike. We haven't achieved that with SysML V1. And in software development, software code is the best example of exactly that. Software code is human readable, is machine readable. We do not have any duplication. And so that is a very powerful concept. And we really have to try to get there, because one of the big weak points of traditional model-based systems engineering is that very few organizations break it out of its silo. Big problem, in my opinion. And again, I said textual notation API here, the same way what Mark mentioned. There are multiple ways of doing that. And depending on your application, you might take one path or the other. But the beautiful thing about SysML v2 is that we have both of it. So the third and last practice that I want to talk about is the automation capability and the integration capabilities. And I find Seaside with the ability to just write a few lines of Python to get to the data, that makes it really powerful. And here you can just see conceptually what this can give you. You can really make sure that the parameterization from your system model is actually leveraged, for example, in your CAD design, which you can use then to compute the mass of your system, and you can feed it back. You can drive dashboards, and there are many possibilities of doing that. And staying in my allocated time frame, this is basically what I wanted to share. What's important here is that Seaside, SysML v2, these tools, those are all puzzle pieces, but we really have to put them together. And there's lots of work that we have to do, but we can look to software development, which to me is incredibly inspirational to show how with openness, with interoperability, with grassroots movements combined with high-level strategic thinking, we managed to achieve things in software that we didn't think were possible before. And I think the same is possible in physical product development, but we really need a foundation on the organization in the development, and there's lots of work to do. And with that, I want to close. I think from the 15 minutes, I have 60 seconds left, so I leave it up to the organizers whether we have time for one question or not. Thank you very much.